Hello everyone, and welcome to today's webinar entitled Virtual Design Space Exploration Methods for Electrical Machines Application. My name is Farnam, and today's webinar has been provided by IanWorks Incorporation as the free webinar series. Today we're going to talk about one of the hottest topics in the world of engineering, especially electrical machines application, because electrical machines are an inseparable part of industry, and as a result we always have to deliver the optimum product to the industry. And as a result we're going to talk about how VDSE methods actually can help us to achieve this goal. In today's agenda, first we're going to talk about the motivation behind the VDSE methods, and after that we're going to move to the steps and components contribute to the construction of the VDSE methods. Then we're going to talk about the techniques available for increasing the efficiency of the VDSE methods that we want to adopt during the design and optimization. And after that we're going to present an example optimization study based on VDSE and IanWorks 2D software. We're going to apply asymmetricity to a conventional IPM machine, symmetric IPM machine, and we'll see how the VDSE method can help us to optimize this machine by applying asymmetricity. We're going to conduct a study, we're going to interpret the results, and we'll see actually how optimization problem can be solved by using VDSE method and also IanWorks 2D. And after that we will have conclusion and references. Without further ado, let's dive into the content. Let's talk about the motivation behind the VDSE methods. As we all know, in all of the engineering design problems, we are facing numerous variables affecting our design goals, right? So, in case of electrical machines, it's no different. As an example, we use an image showing an example asymmetric IPMSM prototype and test bench. And imagine that we want to increase its efficiency, increase the average torque of this machine, while we want to reduce the ripple rate compared to whatever performance it has right now. And as we know, there are numerous variables located on the stator and the rotor that they can have an effect on the optimum objectives that we want to optimize. So it will not be possible for us to create multiple prototypes, and as a result we have no choice but using virtual design space exploration methods, where we need to build a virtual model that is going to represent the features of the design we want to create, and it has to be close to the real life device that we want to manufacture. And by using VDSE methods and actually computer-based modeling techniques, first we're going to prevent the significant cost of manufacturing. We will no longer need to create multiple prototypes, and we can conduct a variety of analysis that we want to have and make sure that performance of the machine is going to be what we desire. And as a result we can make sure that the final product is going to be the optimized one. But there is no perfect solution, and here we have problems such as computer hardware limitations, design to market time and deadlines, and also correlation between different design variables and objectives that all of these factors are going to limit the use of VDSE methods, and we need to consider these limitations during use of VDSE methods. So as a result we have to be aware of how we can optimize the virtual design space exploration process. In order to do that, first let's get familiar with the components of the VDSE methods. As we can see here, there are three main parts actually plays vital. They play a vital role during the process, VDSE process. The first of them is the modeling methods. As we mentioned earlier, we need to develop computer-based models replicating the behavior of real-life electrical machine. And after that, we have sampling methods, where we adopt from various design of experiments techniques to optimize the design space exploration process. We will see actually how sampling method is gonna work and how actually they can help us to reduce the computational cost. And by the end, we will have the search and optimization methods where we apply search algorithms to obtain the optimum design. Let's dive deeper and talk about the specific of these methods. Let's start with modeling methods, where since the electrical machines are design of optimization of electrical machines is a multi-physics problem, we have to consider multi-physics modeling techniques in order to analyze the performance of the machine from multi-physics perspective. First we have thermal model, also we have mechanical model, and finally we have electromagnetic model. In thermal model we can use long parameter thermal network, computational fluid dynamics, and finite element modeling techniques. And as a result we can see how temperature is being distributed in the different part of the electrical machines that we are trying to design and optimize. Also we can analyze the transient behavior of the temperature rise of the machine. And in mechanical model we can analyze noise, vibration, and harshness. We can conduct stress analysis and rotor dynamics and analyze the natural frequencies of the machine. It is very important, especially in case of high-speed electrical motors. But the most important one and common solution for electrical machine design and optimization is the electromagnetic model, where we analyze the electromagnetic behavior of the machine, torque generation, ripple rate, and the features related to electromagnetic performance. And as we understand, it is always going to be a subject of increasing computational cost, because we have no choice but developing electromagnetic model to analyze the behavior of the electrical machines. So as we can see here, there are two main approaches to achieve that. First is finite element modeling, and second is analytical modeling. There is always a trade-off between speed and the accuracy. Finite element modeling method is the most accurate one, and analytical modeling actually increases the speed, while the accuracy of performance prediction actually reduces. But at the end we always have to make sure that the computer-based analysis that we are going to conduct is going to be accurate one. So as a result, finite element modeling is going to be our first choice always. And here in EMWorks Incorporation we provide a software solution for all the needs that we are going to have during the design and optimization of electrical machines. We have Motor Wizard, which is template-based motor design software. We have EMWorks 2D and EMS, where we can conduct detailed finite element modeling in 2D and 3D. And also we have HFWorks, which is software for high frequency simulation devices, and where we can conduct high frequency simulations. And in order to gain more information, you can visit us in emworks.com, and also our team emotorsdesign.com, where we're gonna talk about the electric motors. We have consulting, and we can cover all the needs you have for your electric machines design and optimization problem. Anyway, after we talked about the modeling methods available for electrical machines design and optimization, let's talk about the sampling method, which is a very important part. As we know, each combination of different VDSE variables, including design, circuit, and conditions, can be referred as sample. For instance, we change diameter of the machine, we change the dimensions of the magnet, or we change the current amplitude or current angle in the control of the electric motor. All can be referred as a sample. And as we know, By applying different sampling methods, we can create different distribution in the design space, but the goal is always to retrieve as much as information we want, as much as information as possible, while we want to reduce the number of samples, because number of samples are representing the computational cost and number of simulations that we have to conduct. So by reducing the number of samples and increasing the possibility for information that we want to gain, actually it's going to determine the sampling method that we want to use. And here, for example, we brought 3 sampling methods that they are widely being used in electrical machines design and optimization problems. In the at the left hand side, we have the random solution. As we can see, the samples actually has been distributed in random shape, and we have no control on them. In the middle, we have full factorial or grid search, where 100 samples that we have on our hand actually distributed in a grid form. And on the right hand side, we have the Latin hypercube sampling method, where we want to create a good distribution of the samples that can gain as much information as possible for us based on constant number of samples. As you can see, based on 100 samples, we have created different distributions, and as you can see, it is very important to choose a proper sampling method while we want to solve the design and optimization problem of electrical machines. Okay, after we finish the sampling methods, let's talk about the search and optimization methods. This is the most important part, in my opinion, because we always want to optimize the design based on our design objectives, and we are going through all of these troubles in order to achieve this engineering goal. Actually, we want to create the optimum product, or we want to conduct different studies, and this is actually where our efforts gonna show its results. As we saw, modeling methods has their own trade-off between speed, calculation speed, and their accuracy, and sampling methods are they have their trade-off also between the number of samples and the distribution, and the goal is always to get as much information as we can from the design space. And by combining modeling methods and sampling methods, we can see that they can directly affect the speed and accuracy of the search and optimization process. So we have to choose wisely what kind of modeling methods that we are going to use, what kind of sampling methods we can use to achieve our study, the goal of our study, and the design objectives. But first, we have to understand that the nature of optimization processes and the problems can be changed based on the shape of the optimization we will have. The optimization processes can be conducted in the shape of local and global problems. The global ones actually are much more complex compared to local ones, because we are going to deal with a much larger design space, and as a result we will need to increase the sampling method, increase the sample rate, increase the number of samples, which is directly connected to the sampling methods that we are going to use, and also the modeling methods that we will have for design and optimization. This search space going to be larger, so the time going to be the required computational time and cost going to be going to increase. We have to consider that, and also we have to understand that different variables, different design variables have different effects on objective functions. As we mentioned, ripple rate objectives such as ripple rate or cognitor are much more sensitive compared to average torque against input variables. So we have to make sure that during the modeling we will not gonna have a loss of information, and the modeling process, the sampling method process, and also the optimization process are going to be, all of them going to be accurate and reliable ones. So let's dive into the search and optimization methods itself, how we can categorize them. As we know, one of the important parts of the VDSE is sensitivity analysis, where we conduct different sensitivity analysis techniques such as OAT, one at a time sensitivity analysis, when we conduct 1D parametric sweep, and it will give us a good understanding how actually a design space is going to change based on the variation of the design variables. Also, there are Taguchi based analysis of variance methods, also Pearson coefficient methods. They are available in literature. You can read them in the research papers. But in the optimization step, which is the most important part of the VDSE, we can use two different approaches: deterministic optimization and stochastic optimization. Deterministic is going to refer to methods such as grid search, when we want to search each step in the design space, and also derivative-based optimization such as a Newton method. Also, we have stochastic optimization methods, where we use intelligent algorithms such as NSGA2, multi-objective particle swarm optimization, and also hybrid algorithms. Okay, until now we learned about the components of the VDSE methods and how they are operating, how we are going to use them. But here we want to talk about the techniques that can actually help us to increase the computational efficiency of the VDSE methods. From perspective of search and optimization process, we know that we are going to need a large number of samples to investigate different location of the design space and find the optimum solution. And in case of multi-objective design problems, we have to create multiple Pareto solutions, Pareto optimum solutions. So we have to search the design space in a proper manner. And also we need to create a trade-off between accuracy and computational cost of the modeling methods. So in case of using only finite element models, although we will increase the accuracy of the modeling, the computational cost might become unaffordable. So in this case, we can use cost reduction methods such as surrogate modeling in order to replace the finite element model. And here we're going to talk about how we are going to do that. Surrogate modeling methods are actually the methods that can help us to create a mathematical interpolation models based on the samples obtained by the sampling method, combination of the sampling methods and finite element method. And after that, by creating this model, we can combine this search and optimization algorithm by surrogate model and search and design space for the optimum solution. And here let's talk about the steps that we are going to take by using surrogate based optimization step, which is the combination of modeling method, sampling method, optimization method, and the surrogate building process itself. In the first step, we're gonna define the optimization problem. We have to be aware of the variables, objectives, and constraints that we want to consider during the solving process. After that, in the second step, we're going to establish an accurate finite element model to obtain the objectives and constraints based on the variables. In the third step, we're going to use a proper sampling method to retrieve the data from the design space and create the training data set that we are going to need for construction of the surrogate model itself. After we finish this step, we're gonna train a surrogate model for each objective or constraint at the fourth step. At the fifth step, we're gonna combine the optimization algorithm with constructed surrogate models and search the design space. And at the sixth and final step, we will find the optimum solution that we are looking for. Okay, in order to experimentally assess the proposed surrogate-based optimization procedure by use of VDSE and EMWorks, we have defined an optimization problem that we are going to optimize an initial completely symmetric interior permanent machine by applying asymmetricity and search the design space for the optimum solution by use of surrogate modeling, surrogate-based optimization technique. And here, as we saw earlier in at the step 1, we have to define the optimization problem that we are going to solve. Here we define three objectives. We want to maximize the average torque, we want to minimize the ripple rate, and also we want to minimize the magnet volume. While we're going to use four variables, as you can see here, we have theta S1, theta S2, and theta M. Theta S1 and theta S2 are the angle between the barriers and the Q axis of the rotor, and also theta M is the angle between the middle barrier and the D axis and symmetry line of the rotor. And also we have defined dm, which is distance of the magnet from the center of the rotor, and we're gonna use these variables in order to multi-objectively solve this optimization problem. As we can see here in this configuration, the stator has 36 slots. The operation speed is 1500 RPM. We use distributed winding configuration and also other parameters that has been shown here. Okay, as we saw earlier, the second step is to establish a finite element model that where we are going to EMWorks 2D as an accurate solver in order to predict the performance of the machine based on input variables and different combinations. As you can see here in this model, we have EMWorks 2D simulation, and it takes theta M, theta S1, theta S2, and dm as input variables, and it will give us the average torque, ripple rate, and the volume of the magnet that has been used in the barriers. And as you can see here in this figure, this is the initial performance of the machine in the completely symmetric machine. As we can see, the average torque is around 13.88 Newton meter, but the variation of the torque is equal to 10.92 Newton meter, resulting in 73.93% of ripple rate, which is very high and it's not acceptable. So in order to tackle that, we're going to use asymmetricity and the optimization process in order to minimize this function, and also we want to maximize the average torque as possible as we can. Okay, in the third step, we want to actually create the required training data set for construction of surrogate models. So in order to do that, we used full factorial method, which is a good solution to cover the design space. Since we have a torque ripple rate as an objective function, in our problem, we have to acknowledge that it's a very sensitive objective, so we have to properly search the design space, and full factorial method is one of the methods that can help us to achieve our goal. And we have to make sure that we have enough information from the design space to create an accurate surrogate model. So in order to do that, as you can see, we create a data set. We use full factorial method. We had four variables, input variables, and we assigned 4 levels to each of them, and we created 4-dimensional grid including 256 samples, and we as a result of this sampling method, we created an input data sheet, and based on them we simulated each combination, we obtained the objectives, and we saved the training data set for surrogate model and construction in next step. And here in step 4 we are going to train a surrogate model for each objective and constraint. We use Kriging model, which is very well-known surrogate modeling technique for electrical machines optimization problems, by means of created training data set, 256 number of samples. We created our Kriging model for average torque, ripple rate, and also the volume of the magnet that we are going to use. We made sure that the accuracy is great. We have to be cautious about the accuracy because the surrogate models are, although they are very fast and can help us to create large number of samples during the optimization process in no time, but we have to make sure that they are accurate, and we have to check the accuracy. Here we have an example of ripple rate and average torque has been constructed based on 50 samples here. The plane, actually the surface that we have here actually is representing the surrogate model, and the red dots is representing the samples that we have created in order to create the surrogate models. And after we establish the surrogate models, we move to the optimization itself. We combine the NSGA2 algorithm with surrogate models, and we search the design space. During the design optimization, we have generated 1500 samples, consists of 15 population size and 100 generation, and between from this 1500 samples we obtain 414 Pareto solutions. And as we can see here in this 3D graph, we have our Pareto optimum solutions that they are distributed in the 3D design space of the objectives, and they are distributed in an unpredictable manner. But here, by help of the NSGA2, this intelligent algorithm, and also the surrogate model that we have built by use of EMWorks 2D, actually we obtain this distribution. As we can see here, for instance, in order to achieve higher torque, we have no choice but increase of the magnet volume. But as you can see, the ripple rate has a very unpredictable distribution in both planes, and this is actually confirming the sensitivity of the ripple rate compared to average torque and magnet volume against input variables. This is very important one to realize. So when we want to create surrogate models and search the design space, we have to make sure that we have an accurate models to obtain and capture this distribution in the design space. One interesting observations that our team had during the design optimization of this asymmetric machine, we saw that actually asymmetricity can help us to reach great performances, right? But in order to measure this asymmetricity and the relationship between the performance of the machine, we define two factors called asymmetricity ratio. First is A mid, and also the second one is A side. As you can see here, this factor actually is a representative of the asymmetricity in the middle bridge, and also the A side is representing the asymmetricity caused by the barrier ends, as we saw the location of the theta S1 and theta S2. And as we can see here in the Pareto solutions, there are two areas that actually it's showing us the optimized designs are based on high series asymmetricity ratio, and it's a very great observation. Although as we can see here, there are great number of samples are located below the 5% of asymmetricity, but also we can see that there are optimum designs that no other design can dominate them, and they have asymmetricity factor and ratio of over 20%. And this is a very great and interesting observation that VDSE helped us to obtain and observe. So this is one of the benefits that VDSE had during the optimization of this motor. Well, at this sixth step, we have to choose an optimum design, and in order to do that, we analyze the optimum solutions that we obtain, and we decided to minimize the ripple rate while we are managing a proper value for average torque, and also volume of the magnet that we are going to use. And as a result, this is the shape of the final optimum solution. And as you can see, by measuring the performance of the optimum one, we can see that the ripple rate has been significantly reduced. In this table also, we are comparing the initial value for the design parameters and the final ones. As you can see here, for instance, we have created asymmetricity for theta M and theta S1 and S2, and also we increased DAM, but the average torque actually has increased. The ripple rate has significantly reduced to 19.19%, and magnet volume also has reduced slightly, but at the end, the optimum design is much more better compared to the initial one. Well, at the conclusion, let's have a recap on what we discussed. First, we observed that the limitations and design to market time directly affect the VDSE process. To solve this problem, we reviewed each component of the VDSE, including sampling methods, modeling methods, and search optimization methods. We talked about the concept of them, technical background of them. And after that, we talked about techniques that we can use for an efficient VDSE, create an efficient VDSE method, where we mentioned surrogate modeling, and in order to experimentally assess that, at the end, VDSE and EMWorks 2D has been used for optimization procedure. We applied asymmetricity to an IPMSM, and we saw that we saw that asymmetricity can significantly reduce the ripple rate, while the operation of machine from perspective of torque and the magnet volume has also improved. But by investigating design space, we saw that how actually VDSE method can help us to reach our optimization goals and create an improved design. And here are the references. Thank you for your time, and I hope you enjoyed it. If there is any question, I would be glad to answer them.